Good morning, class. Today we're going to begin our investigation of kinematics. And as you can see, we have two photos here that involve baseball and basketball. And often, sports will always include something to do with the movement of an object. And that, in essence, is what kinematics is a study of. And so some of the terms that we'll be exploring today include the idea of what a scalar and vector is, drawing vectors, and the addition of vectors. So here's the page that we're going to be working on today. So let's commence operations. Kinematics is the study of motion. And so there are several examples here of objects in motion. Often in baseball, pitcher's speed is indicated when throwing the ball. In Formula 1, lap times are recorded. In speed skating, top speed as well as lap times are recorded. And for this cat, acceleration becomes a very important statistic. And so before we can get into all those ideas, let's learn some of the fundamental terms for kinematics. Scalar is a quantity that has a magnitude. Some examples of scalars include mass, volume, time, and distance. A vector, however, is a scalar. But in addition to being a scalar, it includes direction. Vector, a quantity that has a magnitude and a direction. Some examples include displacement, force, and acceleration. And all of these terms we'll learn about very soon. And so often vectors can be represented by using a drawing. To draw a vector, we need a coordinate system and a scale. Let's look at our first example. Agent 001 runs 5 kilometers east. So here's the scale we're going to use. 1 kilometer is 1 centimeters. And these are the steps we're going to take. So we draw our coordinate system here. And this is what the coordinate system looks like. North, east, south, and west. We draw an arrow, 5 centimeters long. Why is it 5 centimeters long? Because we have a simple 1-to-1 ratio. 5 kilometers, 5 centimeters. Because 1 kilometer equals 1 centimeter. Notice the direction the arrow is pointing. It's pointing east. This E in the brackets represents east. And finally, we label the tip and the tail. So often, when drawing vectors, this is called the tail, and this is called the tip. Sometimes, in some textbooks, you'll also see the term head. All right, so here are two other examples. Example 2, Agent 001 walks 8 kilometers. This S in the brackets stands for south. Here we'll use a scale of 2 kilometers equals 1 centimeter. And example 3, Agent 001 walks 2 kilometers. The W stands for west. Here we'll use a slightly different scale. 1 kilometer equals 2 centimeters. So please pause the video now. Work on these two examples for a few moments. All right, I'm going to assume that you've worked on those two examples, and this is what they're going to look like. This line will be exactly 4 centimeters long because of the scale. 2 kilometers is 1 centimeter, so 4 kilometers would be 2 centimeters. 6 kilometers would be 3 centimeters, and 8 kilometers would be 4 centimeters. Notice it points south, Here, this vector also happens to be 4 centimeters long because of the scale, where it says here 1 kilometer is 2 centimeters. So 2 kilometers would be 4 centimeters, and we're asked to draw a vector that is 2 kilometers in length. Notice it points west. So, drawing vectors is one thing. However, often in physics, we'll have to add vectors. And so, how do we do this? Well, to add vectors, we add them from tip to tail. So what exactly does that mean? Let's study this through an example. So imagine we have this vector j that we want to create, and it's equal to g plus s, where g is 3 kilometers east and s is 2 kilometers north. So now, let's see how we would actually draw this. So we draw the 3 kilometer vector first. That's vector g. Notice it points east. Next, we draw the 2 kilometer vector. Notice I've chosen a different color. From here on in, I'd like you to use different colors for different directions. It'll just make adding vectors that much easier. So here we have our second vector drawn, vector s, 2 kilometers pointing in the north direction. So what does this mean, tip to tail? We add vectors, we connect them from tip to tail. Well, it means this. We know that this part of the vector is called the tail, and this is the tip. And for this vector, this is the tail, and this is the tip. So we're going to connect them tip to tail, tip to tail, like so. Finally, we have to draw vector j. Vector j is called the resultant vector. In this situation, it is also called displacement. So, we have vector j drawn in the diagram. Now, please note, this is an error that students sometimes make. The arrow always points from where you started the diagram to where you finished the diagram. So, going back a few moments ago, we started the diagram here, and we finished it here. We drew the east vector first, followed by the north vector. That's why that arrowhead points in that direction. It points in the northeast general direction. And so how do we actually determine the length of this vector? Well, if you were using a scale diagram, it'd be very simple. You would just measure the length and convert it with a scale. But what if you didn't use a scale diagram? Well, we're going to use Pythagorean theorem. Hypotenuse squared equals side squared plus side squared. Or hypotenuse squared, which is j in this case, equals side squared plus side squared. Working through the math, we end up getting j equals 3.61 kilometers. And so that vector is 3.61 kilometers long. If you were using a 1 centimeter to 1 kilometer scale, then this would be 3 centimeters long, this would be 2 centimeters long, and if you made the diagram accurate, this would have been 3.6 centimeters long. I encourage you to try that. Vectors always need a direction. That's important. And so we add an angle. This symbol for the angle is called theta, and that is traditionally the symbol that is used to represent an angle. How do we solve for angle theta? Well, we have to use some trigonometry. Recall that the tangent of theta is equal to the side opposite divided by the side adjacent. The side opposite is 2 kilometers in length. the side adjacent is 3 kilometers in length. We use the function inverse tan, and we end up with the following angle, 33.7 degrees. Putting it all together, we write vector j equals 3.61 kilometers east, 33.7 degrees opening towards the north. Notice, often to represent a vector, an arrow is used. So if we just write j without an arrow, that means it's a scalar. But if we write j with an arrow on top, then that means it's a vector. That means you have to include direction. Remember, that's the only difference between a vector and a scalar. A vector has direction. Now you may be asking yourself, why did we write east and then north? Why didn't we write north and then east? Well, it's basically just look at the way we drew the diagram. We started by drawing the east vector first, and then the north vector second. That's why we wrote east followed by north. Now, with significant digits, since this only has one significant digit, therefore this number can only have one significant digit. Similarly, for the angle as well, one significant digit. Let's look at our next example in our notes. Example 1. Super Spy Agent 001 is on another dangerous mission. While on the mission, 001 runs 50 meters south, then stops on a dime, turns west, and because he's out of breath, walks 40 meters. Find the resultant vector. And when dealing with distances, we often call the resultant vector displacement. So this one's for you. Give it a try. Pause video now. All right, I hope you tried it. Here's the solution. We draw our 50-meter vector first. It's pointing south. Next, we draw our 40-meter vector, and we connect them tip to tail. Notice this 40-meter vector points west. Tip to tail. That's how we attach these vectors. So we draw our resultant. Why does it point in this direction? It always points from where you started to where you finished. Just remember that. That's a common error, once again, that students sometimes make. They're not sure which way to draw the arrow. Always draw it from where you start the diagram, pointing to where you finish. Start to finish. Start to finish. Start to finish. We'll label this vector as the displacement. And now our goal is to determine the length of this vector. And in addition, to determine the angle. Another error that students make is they're not sure where to place the angle. Always place the angle where you started the diagram. Always place the angle where you started the diagram. One more time I'll say that. Always place the angle where you started the diagram. I'd like you to pause the video right now and solve for the hypotenuse, solve for the angle, and fill in these numbers. Okay, I hope you worked on that. The displacement is 64 meters south, 39 degrees west. Or 60 meters south, 40 degrees west. Why only one significant digit? Because 50 meters has one significant digit, as does 40. Next example, example 2. After a skirmish with the Pillsbury Doughboy, the gingerbread man walks 10 kilometers north, then turns and runs 6 kilometers west, and finally jogs 2,000 meters south. Find the resultant vector, also called the displacement. This question is a bit more challenging. Often when students are writing a test, they're under pressure, and they sort of make errors with units. What do I mean here? Well, notice the first two distances are listed with kilometers. Kilometers, kilometers. Here we have 2,000 meters. So the first thing you need to do before you even start this question is convert the meters into kilometers. So recall that 1 kilometer is 1,000 meters. So 2 kilometers would be 2,000 meters. It's very easy to make that mistake when you're under pressure on a test. So write these numbers down, write them down with their units. And you'll see immediately kilometers and meters, they don't match. You have to make them all match. So I'd like you to try this question right now. Go ahead. All right, here's the solution. Remember, tip to tail. 10 kilometers north, 10 kilometers north. Then you turn west and you move 6 kilometers. So on 10 kilometers north, you turn west and you go 6 kilometers. And then you jog 2,000 meters south, which recall is 2 kilometers. Notice the colors here. To represent north or south, we have one color. To represent east or west, we use another color. This may seem like an extra detail, but when questions get a bit more challenging, using colors will really help you explore vectors in an easier manner. So please use different colors when drawing these diagrams. There's our displacement. There's our resultant vector. Recall, we always draw it from where we started to where we finished. This looks like a complicated diagram, and it looks like it's going to be very challenging to figure out this displacement. Let's see how it's done. All right, now that you've given it a try, here's the strategy. We need to make a right-angled triangle. By making a right-angled triangle, then we can solve the displacement. So here's our right-angled triangle. Gone north and then west. Now we have to figure out the length of each of these parts of the triangle. Well, this part's really easy. All right, I hope you've tried it. This part is the easier part of the two parts of the triangle to figure out. Notice it looks a lot like 6, and indeed, it is 6 kilometers. This part of the triangle is a little bit more complicated. But notice we've gone 10 kilometers in one direction, and then we've gone 2 kilometers back. Well, working through the math, that's 8 kilometers. 8 kilometers plus 2 kilometers here gives us the 10 overall. And now we solve this problem just like we did previously, using Pythagorean theorem. In addition, we have to use opposite over adjacent. The tan of the angle theta. Opposite over adjacent. And so there's our general pattern for displacement. Pause the video now, give it a shot. Okay, hopefully you tried that. This ends up being 10 kilometers. And opposite over adjacent, 6 over 8, ends up being 37 degrees. And there's our final answer. Common errors that students make on this particular question is that when they do opposite over adjacent, they'll do 6 over 10. But just recall, it's this part of the triangle, not this length. That's not part of the triangle. And finally, in significant digits, we convert the 37 degrees to 40, one significant digit, because once again, these numbers are to one significant digit. Have a great day. Bye-bye.